All right. So we are recording. Probably be better if we flip the switches. Maybe keep that one on.
You gotta rewire this one.
Yeah, that's probably better. Okay. So this would be lecture 5. Alright, so in today's lecture we are going to solve some example problems for the different theorems and identities we've been formulating, and we are going to show some applications. Last week we talked about the Stokes theorem, and we solved an example where we transformed a surface integral into a line integral, and we showed that the necessary steps. It wasn't the general way of transforming from one to the other. When we wrote the Stokes theorem, I tried to generalize the transformation of a line integral into a parametric integral, but it just doesn't necessarily always work that way. If you are integrating over a line, you just find the best way possible to transform that into an integral of a specific parameter, as in this example that we're going to see today. So, in this example, given the function of x and y, x squared plus y squared, which is just a polynomial function, a 2D polynomial function, show that the integral of the domain of the Laplace of this function is equal to the integral, a closed contour integral over the surface of that domain, or the boundary of that domain, of d phi d normal. Remember, this was a consequence of the Gauss divergency theorem. It's just another way we can write Gauss divergency theorem. And we're going to assume, in this case, such that the domain omega over which we are trying to prove this is just a circle of radius a centered about the origin. So this is x, this is y. So this is a circle of radius a minus a minus a, center in the origin, so therefore the shape of this curve is x squared plus y squared is equal to a squared. Alright? So we're going to show that the left-hand side is equal to the right-hand side, where omega is basically this, and this right here is gamma. Okay, as it works, as the Gauss divergency theorem works in 3D, where omega is a 3D volume and gamma is a 2D surface, it also works in 2D, where omega is a 2D plane and gamma is just simply a 1D boundary, a line. Alright, so this is going to involve an area integration and a line integration, rather than the usual volume integral and surface integral. So, is that clear? So the first we got to do is let's show the left-hand side. Let's see what we get out of the left-hand side. On the left-hand side, the integrand is equal to the Laplace of phi, which is equal to the second derivative with respect to x squared of x squared plus y squared, plus the second derivative with respect to y squared of x squared plus y squared. So the function phi is differentiated twice with respect to x and with respect to y and added together. So the Laplace of phi, what is the second derivative of this function with respect to x? It would be 2. The first derivative is 2x, second derivative is 2. Here the first derivative is 2y, second derivative is 2. So are we clear that we get, well, let's do it in steps. It would be this plus this, which is equal to 4. So we'll be integrating 4. So the left-hand side is equal to the integral over the domain of 4 the omega. And the domain omega is simply the integral over an area xy for the area of xy. Okay, we're in the xy plane, and therefore the area over which we're integrating is just the xy plane. All right, so how do I decide first of all, what is the differential of area in the xy plane? Just dx dy or dy dx, right? And the xy plane, a differential of area would simply be, this is dx, this is dy, and this is the differential of area, which is dx times dy, or vice versa. So we decide whether we use dy dx or dx dy, and what is going to depend the decision on whether we use dx dy or dy dx. It depends on what limits of integrations we get to use, right? At the end of the day, we want to integrate over the circle, okay, or inside the circle, bounded by the circle. So if I decide to use dy dx, the external limits of integration have to be the limits of integration on x, and the internal limits of integration have to be the limits of integration on y. Let's do it that way, for example, dy dx. So the left-hand side has to be the integral of 4 times dy dx. Okay? In the y direction, we're going to go from y1 to y2. And the x direction, we're going to go from x1 to x2. The limits of integration of x go outside, the limits of integration of y go inside. So basically, this is the x-axis. This is dx. And y is bounded by, and this is obviously the y-axis. In this case, the x-axis is bounded by minus a to a, and the y-axis will be bounded by this function right here. It will be from minus square root of a squared minus x squared to plus square root of a squared minus x squared of 4 dy dx. The external limits of integration have to be finite, and the external limits or the internal limits of integration can be functional. So that the end result is just basically a plain old number. So this height right here is plus square root of a squared minus y squared, while this height right here is minus square root of a squared minus y squared. Okay, and now we process that integral. So the left-hand side is equal to the integral between minus a and a. What would be the integral of 4 dy? 4y. That's evaluated between the lower limit and the upper limit, dx. So this will be 8 times the integral between a and a of the square root of a squared minus x squared dx. Okay. Now we need to solve that integral. Well, we might remember what that integral is, or we can just parameterize it, right? An easier way to solve that integral is to do trigonometric substitution. Every time you see a square root and something square inside the square root, a trigonometric identity will do. Okay? So in this case, if I let x be equal to a times, in this case I think I use the sine, yeah. Sine of theta. If I use that substitution, I know I'm going to plug it in there. The a is going to come out as a common factor. It's going to come out of the square root, and this is going to come out of the integral. And I'm going to end up with 1 minus sine of theta, or sine square of theta, right? Which is a cosine square of theta. And that cancels out the square root. So it's an easy fix. Or if you remember what the formula is, then you use it. Or if you have a book, because all the exams and assignments are open books, open notes, then you can just solve that one directly. Or if you have MathCAD, you can do that symbolically and solve it. But if I want to do it by hand in this case, so it would not only take substituting what x is, we need to substitute the x. Therefore, dx d theta is equal to a cosine of theta, and therefore dx is equal to a cosine of theta d theta. Right? And we also need to transform the limits of integration because those limits of integration apply to x. They don't apply to theta. Right? So basically, when x is equal to minus a, then minus a is equal to a sine of theta. Therefore, the sine of theta is equal to minus 1. And when is the sine of theta equal to minus 1? A theta minus 90 degrees or 270 degrees, the same thing. So it's at the negative y-axis. So this would be minus pi half. And when x is equal to a, then a is equal to a sine of theta. Then the sine of theta is equal to 1. And that happens at 90 degrees, pi half. So this integral on the left-hand side is an integral between minus pi half to pi half of, well, a times this times a square minus a square sine square of theta times a times the cosine of theta d theta. Right? And it doesn't end here. I can take this a square as a common factor, take it out of the square root as an a, multiply times this a. So that would be a squares. Square root of 1 minus the sine square of theta times the cosine of theta d theta. So the left hand side is equal to a square. This is a cosine. So I'm going to be integrating the cosine square of theta d theta between minus pi halves and pi halves. Okay? Again, we can put this in the calculator. We have a symbolic manipulator, or we can put it in the, or if we remember the formula. But how do I integrate the cosine square? Remember? Anytime you see a sine square or cosine square, use the formula of the cosine of the double angle. Okay? Remember, such that the cosine square of theta is equal to 1 plus the cosine of 2 theta divided by 2. left-hand side is equal to 8a squared times 1/2 plus cosine of 2 theta divided by 2 d theta. All right, so the left-hand side is equal to 8 squared. The integral of 1/2 d theta is pi over 2. I'm sorry, theta over 2. And the integral of the cosine is positive sine, right? Sine of 2 theta divided by 2, so that will be 4. And I need to evaluate on those limits. And when I evaluate the sine of 2 theta, it will be the sine of pi. What's the sine of pi? 180. On the x-axis is always 0. The sine on the x-axis is always 0. And the sine of minus pi, same thing, it's 180 degrees. So this one goes away. And all we're left with is pi half plus pi half is pi divided by 2, so we end up with 4 pi a squared. So that is the area integral, and ends up being 4 pi a squared. All right, but again, in some of these exercises that I do in class, I want to go over the process of integration or differentiation, even though some of these might be obvious, or even though some of these may be done automatically by a calculator or by or a spreadsheet that has a symbolic manipulator. We have Maple, college-wide license, that has a good symbolic manipulator. Mathematica has a symbolic manipulator. And you're allowed to use all this software. So when I give you an assignment or an exam, you don't need to show this work if you don't have to. However, if you just show the solution and you made a mistake in the setup of the problem, then there's no way for you to get partial credit. If you try to show the process and made a mistake on a sign or something, then it's easier for me to assign partial credit even if you end up with the wrong result. Is that clear? Okay. So I'm not going to force you into remembering how to do any of these by hand, but I find it sometimes useful to just go back and exercise these things, at least in class. All right, so that was the left-hand side. The right-hand side, and the right-hand side, the integrand is the phi dm. Which, remember, is the gradient of phi dotted into the normal vector. Such that the gradient of phi is equal to d dx of x squared plus y squared in the x direction plus d dy of x squared plus y squared in the y direction. So this, the vector, remember, a gradient yields a vector. So the gradient of phi is equal to 2x in the x direction plus 2y in the y direction. The normal vector to, in this case, a line that surrounds the area, the boundary of this domain, will be the gradient of a function that defines the domain divided by the magnitude of the gradient of the function that defines the domain. That's always the case. Such that the function of x and y that defines the domain has to be the level curves of some function of x and y, and that would be x squared plus y squared minus a squared. So we just make that function equal to 0. It could be x squared plus y squared minus a squared, or it could be the opposite. The opposite would also be 0, a squared minus x squared minus y squared. But one will yield the normal vector pointing out, and the other one will yield the normal vector pointing in. So we'll get a negative of the result. So we have to make sure that the normal vector points out. We'll see what we get out of these. So the gradient of f is the gradient of this function, which happens to be the same thing, 2x and the x plus 2y and the y. By the way, this is a coincidence that the gradient of this function is the same gradient of phi. Okay, they don't have to match at all. It's just a coincidence that the area omega, that the domain omega, is defined by a function that has the same algebraic form as the integrand. The gradient of f has nothing to do with the gradient of phi. They're two completely different things. This is a function that is passing by. This is a potential function that is passing by the domain. And this gradient of f is just the domain itself. The magnitude of f is equal to, well, the square root of 2x squared plus 2y squared. So that would be that the 2 can come out x squared plus y squared. Therefore, the phi dn is equal to 2x in the x direction plus 2y in the y direction times, or dotted into the normal vector, which is 2x in the x direction plus 2y in the y direction, divided by 2 x squared plus y squared. And as you can see, this is the correct normal vector. This is a normal vector that points out of the domain. You pick a value of x and y on that circle, and this will give you a positive number, a positive vector, in the x and in the y direction, if x is positive and y is positive. It will give you a vector that is negative in the x direction if x is negative. So it is actually pointing to the outside of the circle. Is that clear? Alright, so the 2 and the 2 go away, and this actually ends up being it's twice x squared plus y squared. This 2 and goes out with these 2, and this is simply twice the square root of x squared plus y squared. So this is what we're trying to integrate. So the right hand side, which is equal to the integral over the boundary of the phi dn, d gamma, is equal to the integral over the boundary of twice square root of x squared plus y squared d gamma. All right. Now we need to parameterize this curve. Okay, we're taking a line integral, closed contour line integral. So that's gamma. This is a piece of gamma. Right? So normally you would say gamma is, normally what you would say is that gamma is equal to, well, if you focus in there, you would say that gamma is equal to the square root of a little bit of dx plus a little bit of dy. So gamma, well, the line is a hypotenuse of a triangle whose sides are a piece of dx and a piece of dy. And then you can parameterize x and y in terms of a curve to find what that integral does, and then integrate the whole thing. So in this case, the easy way to do it, again, we have a square root with things that are square inside, so we can parameterize just like this. We can say that x is equal to a cosine theta, while y is equal to a sine theta, because gamma is defined by the curve x squared plus y squared is equal to a squared. So if we parameterize a and y like this, it would actually fit into this curve. And since this is a closed contour integral, then theta will go from, is such that 0 so it would go from 0 to 2 pi. Right? So let me think about this. All right. So if I say this is the right parameterization, because if I use this parameterization, it would give me an identity on what the curve is defined as. Then I can say since d gamma is equal to the square root of dx squared plus dy squared, such that dx is equal to minus a sine theta d theta, and dy is equal to a cosine theta d theta. I am getting that from here. Dx d theta is minus a sine theta, and dy d theta is a cosine theta d theta. Therefore, d theta is equal to the square root of minus a sine theta d theta squared plus a cosine theta d theta squared. So d theta is equal to, I'm going to get an a squared, that's going to come out as a common factor, that's an a. I'm going to get sine square of theta plus cosine square of theta, and I'm going to get a d theta that can come out as a common factor. And this is 1. And therefore, d gamma is just simply a d theta. And I can always do that regardless of what that line is. If I can find a parameterization that fits the curve, I can find out the differential of gamma as the square root of dx squared plus dy squared. I can even do that in 3D. So, essentially, the right-hand side will then become the integral from 0 to 2 pi of the integrand, which is twice x squared plus y squared, and d gamma, which is a d theta, where x is given by a cosine theta and y is given by a sine theta. So the right-hand side is equal to the integral from 0 to 2 pi of twice square root of x is equal to a cosine theta squared plus a sine theta squared a d theta. And as you can see, you can take the a out of these. You can take the other a. So the right-hand side will be twice a squared times the integral from 0 to 2 pi of the square root of cosine square of theta plus the sine square of theta d theta. This is 1. And now I'm taking the integral of 1, which is theta, evaluated between 0 and 2 pi, which is 2 pi, right? So the right-hand side is equal to 2a squared times 2 pi, and therefore the right-hand side is equal to 4 pi a squared. It's exactly the same thing as we found on the left hand side. All right. Any questions? Okay, so let's look at some applications of where these Gauss divergence theorem and Stokes theorem can be applied, and actually comes into play in any or in every phenomena in mechanical engineering, whether we're talking about solid mechanics or fluid mechanics or heat transfer or simply just mechanics, kinematics or dynamics. The Gauss divergence theorem and the Stokes theorem is going to have a relevant application, and it's going to actually applications to fluid flow. Let's look at fluid flow applications. So let's say that we have a domain omega, and this domain omega is surrounded by a surface gamma, of which I can focus on a specific d gamma, where there is a normal vector pointing out. That normal vector is going to define the normal direction out of the domain. And let's say that I have a fluid flow passing by. So this is a fluid flow with velocity v. And that velocity v is a vector field that is a function of x, y, and z. It can also be a function of time. So if I wanted, for example, to derive or formulate an equation relevant to fluid flow that defines conservation of mass, I would apply the general conservation law that applies everywhere in engineering, where I say, well, everything that goes into that control volume minus everything that goes out of that control volume plus whatever is generated inside that control volume is equal to the amount stored within the control volume. That is a conservation law that applies to anything. Not only fluids, it applies to anything you can think of. You define a control volume and quantify everything goes in minus whatever goes out plus whatever is generated. You get the amount stored. You can also express this in rate form. And in rate form will be, well, the rate at which whatever amount is coming in. And when I say whatever, it can be mass, it can be momentum, it can be energy, it can be entropy, it can be anything. Money in the bank. CD. Okay. All right, yeah, it really applies to money in the bank. If you count
minus the generated in the start.
Well, the generator is the interest rate. Since the control volume is your bank account, whatever you put in minus whatever you take out over time, plus whatever is generated internally by interest. Well, the generation can also be negative because you can be actually charged fees and stuff. It's equal to the rate of change at which the money changes on the bank account. So it's universal. Okay. So let's say that we want to apply this principle to, say, conservation of mass. Conservation of mass basically says that mass cannot be transformed or destroyed, it cannot be destroyed or spontaneously generated, unless there's some sort of chemical reaction, nuclear reaction inside. Not chemical. Chemical reactions do not generate mass, only nuclear. But let's say in a regular fluid flow setting, the amount that goes in minus the amount that goes out. So this is the total, the net rate of mass coming in. I'm going to call this M. The net rate of mass coming in and out of the control volume is minus the integral over the surface of rho v dot n d gamma. Okay, and let's try to dissect that particular term and see why is that the amount of mass leaving and entering. It's actually the net amount, in minus out. Okay, first of all, we define this as in minus out, but it's negative because the normal vector always points out. The way we define the normal vector, according to our sign convention, the normal vector always has to point out of the control volume. So if you multiply the velocity field times the normal vector and you get a positive number, it's because that velocity is leaving the control volume, right? If you multiply the velocity times the normal vector and you get 0, it's because basically it's not entering or leaving during that or in that particular space, in that particular differential of gamma, because they're parallel to each other. Like in the walls of a pipe, for example. In the walls of a pipe, V dot n is equal to 0. At the inlet of a pipe, V dot n is negative, right? Because the normal vector points out and the velocity is coming in. So they're opposite to each other. All right, so the total integral over the entire boundary that surrounds this domain, the negative of that is the amount of stuff coming in minus out. This is the mass. Why is this the mass flow rate? Well, we have density, velocity, area. That's mass flow rate. Okay? So that accounts for the entire amount of mass, net amount of mass, entering and leaving the boundary. And this is in kilograms per second. As you can see, if you use SI units, that would be density, velocity, area. But let's just say that for the sake of argument in this particular problem, the amount of generation of mass is equal to 0 because there's no nuclear reactions in the domain. That would be the only way that we could possibly generate mass. Where energy somehow will be transformed into mass, but that's not happening. And the amount of mass stored on the control volume, this is CV. The amount of mass stored in the control volume will be the integral over omega of d rho dt. Oops, sorry, not dt. d omega. Alright? It's how density changes as a function of time within every point inside the domain integrated over the domain. What are the units of these? Density times volume. Remember, omega is volume. Density times volume gives you kilograms, right? Gives you mass. Mass divided by time is kilograms over seconds. So now we have a consistent set of units on the left and on the right. So and this is also kilograms per second. So when we put this back into conservation, we end up with minus the integral over the domain of rho v dot n d gamma is equal to the integral over, this is the boundary, this is the domain. The left-hand side is the amount, the net amount in or out, and the right-hand side is the amount stored. It's mass storage. which would only be possible. Remember, this is a control volume, and a control volume is a fixed window, or it's a fixed volume. It doesn't change inside. So the only way for mass to accumulate inside the control volume, if you're pushing a fluid flow through this control volume, the only way that it can accumulate is if the density changes over time, right? If we're talking about an incompressible fluid, like water, for example, you pass that water through that control volume, and you're not going to have any mass accumulation because whatever you put in is going to go out instantaneously on the other side. You have to have an inlet and an outlet somewhere. If you're putting mass in, it has to go out instantaneously on the other side. If the fluid is compressible, you put fluid in. The control volume is not changing in size or shape because it is a control volume after all. But you're putting mass in, and then that mass accumulates in the form of density changes, and at some point it's going to comply and leave through the other side. But the instantaneous amount of mass flow rate coming in is not equal to the instantaneous amount of mass flow rate coming out because the flow could be compressible. All right? So this is just basic fluid mechanics, but I'm just trying to do the mathematics of how do we go from here to an equation. This looks like an integral equation. We don't want to mess with integral equations, so we're going to turn it into a differential equation. So to turn it into a differential equation, we apply the simple trick of taking the left-hand side, use Gauss divergency theorem on left-hand side. The Gauss divergency theorem says that we can transform a line integral, or that's a boundary integral, into a domain integral. So we have rho v dot n, then can be transformed into the divergency of rho v. The omega is equal to the rho dt, the omega. All right? And now I have a domain integral on the left and a domain integral on the right, and I can put them together into a single domain integral and say, well, this is d rho dt plus the divergency of rho v. The omega should be equal to 0. Okay? And now since omega cannot be 0, so since omega is different than 0, then the only choice for this to be true is if the integrand is equal to 0. And this is the differential equation for conservation of mass or continuity equation. All right? So we went from an integral equation here to a differential equation, which is more solvable. Because we know how to solve differential equations. Integral equations require a little bit more manipulation, usually numerical techniques. We can solve that equation, or try or attempt to solve that equation using numerical techniques as well. But this is an equation in strong form. We refer to differential equations as equations in strong form because they come from a conservation principle. They satisfy relationships. Okay, they satisfy constraints. This is an equation that satisfies the laws of conservation of mass, but it doesn't do so on a global sense. That equation up there is a weak form of this equation. It's called a weak form because it doesn't satisfy the equation at every point, but it does so in the global sense. It satisfies conservation of mass in the global sense, in the domain and on the boundary surrounding that domain. Okay? There are modeling methods that start from this form of an equation, from the weak form, the finite element method and the finite volume method, use that as a point of departure to solve the equations. That's what's under the hood of whatever methodology you're using to solve a fluid mechanics problem, a CFD problem. And there's some other methods, like the finite differencing method, that uses this as a point of departure. Okay? So finite differencing techniques, which are the oldest numerical techniques, use this as a point of departure for the formulation of the method. And finite elements and finite volumes use that, the weak form of the equation, to get to the answer. Okay? Finite differencing method uses the strong form, and therefore they give you solution that is constrained and is accurate at every point. However, they actually lack global conservation. Therefore, you might solve a problem of fluid mechanics using finite differencing and get right solutions at every point and find out that you're losing mass. Okay? Because in the global sense, the numerical error is going to induce the methodology to lose mass or gain mass. Okay? Mass is not really truly conserved at the end of the day. But if you depart from there, mass is being conserved automatically in the global sense. Okay? In the weak form of the equation. Strong form, weak form. Okay. We'll see a little bit more of that down the road, especially on the follow-up to this class in the spring. We'll just do modeling. We'll take equations like this and try to get to answers by formulating them in terms of a numerical technique. All right. Now, can we solve that equation? The next part of this class, the second portion of this class after exam number 1, we'll start by looking at differential equations and trying to solve them. Now, this is an equation that has how many unknowns? The density is an unknown. It's differential of density, so it's implicitly a function, right? And the velocity is 3 independent unknowns. Remember, the velocity has a u, the v, and the w component in general. So this is an equation for 4 unknowns. That's not solvable. It's underdetermined. So we need 3 other equations to complement the system, and that's what we call the Navier-Stokes equation. In the Navier-Stokes equation system, what we do is we do the same exact thing. We apply conservation, but instead of doing conservation of mass, then we do conservation of momentum. Newton's second law. And when we do conservation of momentum, we end up with 3 additional equations. Okay? Now we have 4 equations for 4 unknowns. Density, velocity, or the 3 components of the velocity. And there we go. So then we can attempt to find either analytical or numerical ways of solving for these. Now, if we start with that equation and say, well, let's assume that if flow is incompressible. If flow is incompressible, what does that mean? That density is a constant, or can be considered a constant. Now, for a flow to be incompressible, the fluid doesn't have to be incompressible. And we're getting into the details of the physics here, not into the math. But an incompressible fluid, such as a liquid, for example, water, is always an incompressible flow. Okay? Water always flows as an incompressible flow because it is an incompressible fluid. You cannot change the density of water. You take density at sea level, and it's 1,000 kilograms per meter cube. You take it down in the Mariana Trenches, 11 kilometers below the sea surface, and the density is really, really close to 1,000 kilograms per meter cube. So therefore, the density of water is fixed at 1,000. Okay, so we cannot change it. But for example, air, which is highly compressible, sometimes can actually flow as an incompressible fluid under certain restrictions and constraints, on conditions, right? And in fluid mechanics, the limit is the Mach number. If the Mach number is less than 30%, less than 0.3, we can always assume that air flows as an incompressible flow. Okay? Beyond 0.3, then it actually flows as a compressible flow, and there's compressibility effect, which change the whole thing dramatically. But anyways, when you can assume that the density is equal to a constant, then this equation turns out to be so this one goes to 0, right? If the density is a constant, it doesn't change as a function of time. And because this is a constant, it can actually be taken out of there because it's a constant. And then that leads to the divergency of the velocity be equal to 0. And that's where it comes from. So for incompressible flows, the velocity field is solenoidal. That means divergency free. Right? When we define the operator divergency, we said that those vector fields whose divergency is equal to 0 are called solenoidal fields. That comes from electromagnetics. We'll see how that applies and why those vector fields are called solenoidal, but now we know that in fluid mechanics we know where this comes from. If I tell you that in incompressible fluid flows the divergency of the velocity is equal to 0, that doesn't make any physical sense. Okay, why is the divergency of the velocity equal to 0? Well, it's all a consequence of everything that we did here. Okay, the velocity field has to be divergency free. That means that the derivative of the velocity in every direction of the vector field, they all have to cancel out in order for there not to be accumulation, for the velocity field, for the flow field to be incompressible. Okay, now furthermore, if flow is irrotational, remember we call this that the curl of the vector field V is equal to 0. This is a big restriction. This is a big assumption we're making here. The assumption of incompressibility on a vector field is not far-fetched. Again, if it's a liquid, that's always the case. If it's a gas and it flows below 30% of the speed of sound, then that's also the case, always. So this is always true. We don't need to make any assumptions unless we have very fast flows of a compressible fluid. In the case of irrotationality, this is a big assumption. Okay? Saying that a flow is irrotational is almost equivalent, it's actually equivalent, to saying that the flow doesn't have any viscosity, which is not ever true. All right? But for the points of view of mathematics, this is the first attempt that people could use to actually solve fluid flow problems. Because the equations of fluid flow are very complicated. This is just one of the equations. The other three equations in Navier-Stokes are nonlinear, partial, and coupled, which makes them impossible to solve. So people say, well, why don't we just make some assumptions, some simplifications, like they always do, say, can we get to an answer? And this is the first thing they could come up with. Because if you say this, then this combination of incompressible, which means divergency is equal to 0, plus irrotational, that means that the curl is equal to 0, means ideal fluid flows. All right? So ideal fluid flows are those who are governed by incompressibility and irrotationality. Incompressibility, that's okay, that's physically possible. Irrotationality for a fluid flow, that's not really true. It never happens. Because you can never say that viscosity has no effect, especially close to surfaces. Maybe in the far field, in the middle of a fluid flow that is far away from the effects of surfaces, viscosity might not have too much of an effect, but in general, viscosity has an effect, otherwise there will be no shear, there will be no friction, there will be no drag. All right, but if we start from this point, then we could say, well, because the flow field is irrotational, remember what happens when a flow field is irrotational? Then there is a potential phi such that the velocity is the gradient of phi. For conservative or irrotational fields like this, we can always define the v in terms of a scalar potential function phi, like this. You remember why that's possible? That's only possible when the curl of v is equal to 0. If the curl of v were not 0, that function doesn't exist. And it only exists because of that mathematical identity. Recall the identity that says that the curl of the gradient of any function is equal to 0. Okay, that's a cause, not a consequence. There's a mathematical identity, you can prove it, that says if you take any function, you pick a function, whichever one you want, take the gradient of that function, and then take the curl of that gradient, you'll always get 0. We already proved that, right? Now, because of that, anytime you say that a flow field is irrotational, then that function should exist. Now it became a consequence, not a cause. All right? So we can actually define v in terms of that potential because the velocity field is irrotational. Okay. So if that's the case, now use the incompressibility condition that says that the divergency of v is equal to 0. And then what would happen? Therefore, the divergency of the gradient of phi is equal to 0. And what is the divergency of the gradient? How do we call this operator?
Laplace.
The Laplace. So now the Laplace of phi is equal to 0. So this is a Laplace equation. For phi. So that means that potential, or velocity potential, phi is harmonic. Any function that satisfies Laplace's equation is called a harmonic function. All right. So now instead of trying to solve the continuity equation, the Navier-Stokes equation, we can just try to solve the Laplace equation for phi under certain boundary conditions and constraints. We solve the Laplace equation, we find phi, and with phi we construct v, because v is the gradient of phi. Right? Makes it easier because this is a linear equation. It's well known, it's well posed, and there's many analytical methods to solve that equation. Okay. Furthermore, define a stream function. Psi such that u is equal to d psi dy, or v is equal to d psi negative of d psi dx. Remember that the velocity field is u in the x direction plus v in the y direction. We're doing this in 2D. All right, we already defined up here, we defined velocity in terms of phi. Right? So this means up here, it means that u is equal to the phi dx and v is equal to the phi dy. Now we are defining u and v in terms of psi, or basically we're defining the stream function in relation to the velocity. Using the incompressibility condition that says that this is equal to 0, du dx plus dv dy is equal to 0. That's what the divergency of the vector field is, du dx plus dv dy. So that makes then d dx of u, which is d psi dy, plus d dy of b, which is minus d psi dx, equals 0. And that will be that the second derivative of psi, dx dy, minus the second derivative of psi, dy dx, is equal to 0. So this basically proves that 0 is equal to 0, meaning that the definition of psi automatically satisfies compressibility. So, or incompressibility. Definition of psi automatically satisfies the continuity equation. We don't need to do anything with it. Right? Right. Now using the irrotationality condition. Irrotationality condition. So what does the irrotationality condition say? That del cross V is equal to 0. And therefore, when we do the curl of the vector field of the velocity field, we get E, Y, dz, d dx, d dy, d dz, and then we get U, B, and W is equal to 0 because this is a 2D vector field. Ex, Ey, and this should be equal to 0. So the curl of the vector field, if we multiply, you see the 0 comes always into play. We're talking about the differential of y of 0 with respect to y, which is 0, the differential of u with respect to z, which is 0, and the differential of v with respect to x and the z direction. The only term that survives is the x term, or the z term, I'm sorry. It would be dv dx minus du dy and the z direction, and that needs to be 0. That's what irrotationality means. In a 2D vector field, the curl only has a component in the z direction, and that is the z component of the curl, and it has to be 0. So plug in definition of psi. Remember psi we defined up here as u being d psi dy and v being d psi dx. So that means that d dx of v, which is minus d psi dx, minus d dy of u, which is d psi dy, and the z direction must be equal to 0. So that means that minus the second derivative of psi with respect to x squared plus the second derivative of psi with respect to y squared in the z direction must be equal to 0. And that means, essentially, that the Laplace of psi is equal to 0. So this is also Laplace equation for psi, which is an equation that is easier to solve. And this implies that the stream function is harmonic. So both potential function and stream functions are harmonic. And we can later prove that equipotential lines that means the psi equal to constant line are always perpendicular to streamlines. Those are the lines that psi equal to a constant. So basically the potential function phi is what drives the flow. The potential function, the potential lines or equipotential lines are always perpendicular to the streamlines. Basically the potential is what drives the flow. The potential is equivalent to the pressure in this formulation. You have high potential, low potential, and the flow will just basically follow those lines. So basically we have two Laplace's equation, one for phi, one for psi, and those equations can be used, well, we can solve those equations for phi and psi, and then we can use phi and psi to reconstruct the velocity field. Okay, so that gives us access to possible solutions of fluid flows that were not possible before this particular set of arguments for ideal fluid flows were made. Okay, furthermore, after these it was conformal mapping, so if you can actually find a solution for a fluid flow in a circle, for example, then you can actually use conformal mapping to change that circle into something else, and then the solution applies in that other plane, the transformation plane, and then that's how they came up with solutions of fluid flows on airfoil types of shapes. Okay, so the first attempts to solve fluid flow problems was done by this particular set of arguments here. So in conclusion, in summary, basically, for ideal fluid flows, what we have is incompressibility and irrotationality. This has to be true. Incompressible, irrotation. This leads to the Laplace of phi is equal to 0 and the Laplace of psi is equal to 0. This is the potential function and this is a stream function such that v is equal to u in the x direction plus v in the y direction as the components, and u is defined as the phi dx, or u is defined as d psi dy, and v is defined as the phi dy, or minus d phi dx. And that's it. So this is in summary what ideal fluid flows are. All right. And this all came from an implementation of Gauss divergence theorem that led us to find out that when a flow can be considered to be incompressible, the governing equation is divergence of B is equal to 0. All right. Are there any questions? All right, so I'll see you Thursday.
I'm gonna have a terrible one.